Even the layman knows the first one, the first series, that the harmonic series diverges. But what about this? What do you think will be the sum of the series? Where basically in denominator you have the prime numbers. So we will analyze this series in this video, and I think this is a really beautiful result that I have come across today, and I wanted to share it with you amazing guys. Yeah. Now, first of all, if someone doesn't have the idea why this diverges, let me just give a brief intro about that one too, and then we'll go to the series. Okay, now there's quite a good proof of why this should diverge. So let's say you have 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 and so on. Right. Now what I will do is I will group these terms. This first two terms. Well, let me write quite a few. 1 by 8, 1 by 9 up to 1 by 16 plus 1 by 17 up to 1 by 32 and then goes on. Yeah. Okay, now I will group this for two terms, 4 terms, and then over here 8 terms, 16 terms, and then 32 terms, and so on. Now we know that this sum will be greater than 1 plus 1 by 2 plus 1 by 4 plus 1 by 4. Note that I'm writing 1 by 3 is greater than 1 by 4. I think that's obvious, because if you just reciprocate, 3 is less than 4, right? So that's why this should be true. Yeah. And also because if it's a bigger number denominator, that will be smaller. That's obvious. Yeah. So then plus this should be bigger than 1 by 8. 1 by 8 plus 1 by 6 bigger than 1 by 8. Now the why I'm doing like this will be obvious in some minute. Again, now I 1 by 9 is bigger than 1 by 16. So there will be 8 1 by 16s, right? After that there will be 16 1 by 32s and so on. And now this new sum, which is lesser than the harmonic sum. Yeah, now this is 1 plus 1 by 2. There are 2 1 by 4, so that's 1 by 2. There are 4 1 by 8, so that's 1 by 2. There are 8 1 by 16, which is 1 by 2. Again 1 by 2, 1 by 2, 1 by 2. Now notice that we can get this series to be however large that we want. Like if you just go on increasing the number of terms to be sufficiently large, then we can get any sum for this expression. Yeah. So that means it increases without boundary. Even if let's say we think a boundary, and to get that boundary, if we increase and make n sufficiently large, we will go beyond that. So you can just see that because this 1 plus 1 plus 1 plus 1 plus 1. So if you just go on adding 1, that can go however large as you can, right? So you can say that this new series diverges. That means it becomes really big, goes to infinity. Yeah. So since this diverges, goes to infinity, now this harmonic series is bigger than this new series. And the new series diverges, that means this harmonic series should also diverge, right? So this is how we can prove that the harmonic series diverges. So you get the proof, right? But now the interesting part is, what about this series where we have prime numbers in denominator? So if you have to write this is sum of primes 1 by p. This is how we write this. It's easy. Now for this one, what I will do is I will first try to give you a relation. Yeah, and to find this, the same harmonic series will be invoked. You will see that. Okay, so first of all, I will write something over here. 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5. This series will be equals to okay, so 1 by 2 to the power 0 plus 1 by 2 to the power 1 plus 1 by 2 to the power 2 plus 1 by 2 to the power 3. Sorry, and up to all the powers, the 4 2 to the power 4 to the 5 and all the powers, times 1 by 3 to the power 0, 1 by 3 to the power 1 plus 1 by 3 to the power 2 plus 1 by 3 to the power 3 and all the powers and so on. Again over here also 1 by 4 to the power 0, 1 by 4 to the power 1, and so on. 1 by 5 to the power 0, 1 by 5 to the power 1, 1 by 5 to the power 2, and so on and so on. Yeah, it goes to infinity in both sides. I'm sorry, and it goes. Okay, now first of all, see why these two are equivalent. Yeah, so over here, if you just multiply the first, if you try it like multiply all of them, so if you multiply the first, we get 1 by 1, right? Now over here, if you take 1 by 2 and all the first terms, you get 1 by 2. And if you just take first term from here and over first term from all the others, you get 1 by 3. First term from here, second from here, and first from others, you get 1 by 4. So you get all those numbers, right? Wait. No, there's a mistake. I wasn't trying to include 1 by 4 over here. Sorry. I was just trying to include primes. In this way, you will get like the entire series in the first term itself. Okay, so over here, 5 to the power 0 plus 1 by 5 to the power 1 plus 1 by 5 to the power 2 plus 1 by 5 to the power 3, and so on. And now 1 by 7 to the power 0 plus 1 power 1 plus 1 by 7 to the power 2, and so on. Yeah, okay, now this was what I meant. This is 0, this is power 1 by power. Okay, now first of all, okay, now if you just take first term, we get 1. Now over here, we can get a fraction with any number in denominator. So how that works is, we know that any number can be factorized as prime numbers, right? So let's say a number, let's say 12 has factorization of 2 square times 3, right? So what I need to do is take 1 by 2 1 by 2 square from here, 1 by 3 from here, and all the powers of zeros from here, all the numbers with power zeros from here. So that gives us the required number. Let's say if we want to get 26, this is 6 times 21, that is 6 times 3 times 7, right? And so this is again 2 times 3 square times 7. So what I can do is take 1 by 2 to the power 1 from here, 1 by 3 square, and 1 by 7. So that will give you this number. So this shows that any number can be achieved by taking the required terms, or let's say appropriate terms from each of the following series. Yeah, and just multiply them and get the required term that you want over here. So this shows that due to the due to the unique prime factorization of all the numbers, this is possible. Okay, now after you get this idea, this is an easy idea. I just explained it in a difficult way. I'm sorry for that. I made it more complex, I guess. Now this sum from I equals to 1 to infinity of 1 by I can be written as, now if we write it as product over all the primes of 1 by p to the power 0, 1 by p to the power 1, 1 by p to the power 2, and so on, right? Now okay, so we can sum this, since you know that for primes, for any primes 2, 3, 5, 7, any primes, 1 by p is always less than 1, right? So we can use geometric series to find the sum of this, which gives us a product over prime, and now first term is just 1 and the ratio is 1 by p, so 1 by 1 minus 1 by p. This is product over prime of 1 by 1 minus p inverse, right? So this is our sum from I equals to 1 to infinity of 1 by I. I think most of you should have already seen this product also from the zeta, that zeta of s, which is supposed to be sum from I equals to 1 to infinity of 1 by I to the power s. This is also equals to product over primes of 1 by 1 minus p to the power minus s. Yeah. To derive this one, we used a different way, but this one was easier, so I used this approach for this one. Now, after we know this, what I will do to find the sum of inverse primes is I will take log in both sides. Yeah, I think that makes sense to you guys too. If we take log in both sides, log of this is sum from I equals to 1 to infinity of 1 by I will be equals to sum over primes of log minus log, because this is, I'm going to inverse it. Yeah. After this, we have converted sum. Now you can use the like Taylor series of log, because again, because the modulus of p inverse will be less than 1, so I can use Taylor series. So, sum from I equals to 1 to infinity of 1 by I, this will be equals to, now this is, again, if you Taylor series, this will just be 1 by p by 1 plus 1 by p square by 2, because minus log of 1 minus x, its Taylor series is x plus x square by 2 plus x cube by 3 plus x4 by 4 and so on, right? So we'll use that. Over here it's 1 by p cube by 3, 1 by p to the power 4, and so on. Okay. Now we have to find the sum of this series. Now what I will do is log from x1 to infinity of 1 by I is equal sum over p. See, we have got the required sum over here. Sum over primes of 1 by prime. So you see, this has come into action now. I think we are closer now. So this is 1 by 2p square. Sum over primes. Yeah. Primes of 1 by 3p square. Plus, and it goes in, plus sum over primes of 1 by 4p to the power 3 power 4, and this goes in, right? Now what I will show it to you guys, that still now, because I know that we cannot like distribute it like this, if this one of the sum will diverge, but 8 we don't know if it diverges or not, so we are assuming this converges. So assuming this is converges, so we are like breaking this into individual sums, right? All those will converge, yeah, because of the fact that sum of over natural numbers, over natural numbers of 1 by n to the power x for x greater than 1 converges, so this should also converge. Again, I think you see that why. Now what I will try to show you is this sum over here. I'll prove it later on, but for now I will just say that those sum over there, of course it's greater than 0, right? Because all these are positive numbers, but this will be less than 0.423. I will show you later on why. So all of these are converging. This whole sum is converging, and that will be less than 0.423. And yeah, I will show you this at the end of the video. But for now, just believe me. Now, if you believe me, now we know that this is log of sum from I equals to 1 to infinity of 1 by I is equal sum over primes of 1 by p plus 0.423. Now I think you see there's a problem. This harmonic sum diverges, right? In log, so that goes to infinity. So log of infinity is also infinity. Now you see that a diverging sum, log of infinity is infinity. So a diverging in infinite value minus 0.423 is this sum. So that means this should also diverge, right? So since this is a diverging sum and this goes to infinity, so that's why this is also go to infinity, and hence we conclude that this diverges. And so that's why the sum over primes diverges. This was given by Euler, not me. Yeah, but yeah, it's a good one. Now let's try to prove that this whole sum is converging on. Now let's try to prove this. It's not that hard actually. So sum over primes of 1 by 2p square plus sum over primes of 1 by 3p cube plus sum over primes of 1 by 4 to the power 4 and so on, right? Now what I can do is, we know that this sum is greater than 0. We don't need proof for that because all numbers are positive. So now I will say that this sum will be lesser than sum over n equals to 2 to infinity of 1 by 2n square plus sum from n equals to 2 to infinity of 1 by 3n cube plus sum from n equals to 2 to infinity of 4n to the power 4 and so on. Yeah, I think you see why this should be lesser than this one, because over here a few terms of the sum below are not there, because maybe over here we have n as 3, n as 4, n as 6. Those terms aren't there in the this sum, this prime sum, right? So that's why this will be slightly lesser than this one. Now we'll see that this has the sum of 0.423. Now to show that, let's see how we do that. Now first of all, let me write it properly. N equals 2 to infinity of 1 by n square by 2 plus 1 by n cube by 3 plus 1 by n to the power 4 by 4 and so on. Yeah, and then wait, why did I write less than over here? This should have been equal to, I'm sorry for that, this should have been equal to. Okay, now after this what I can do is, now I can say that this is sum from n equals to 2 to, wait, I think I missed something. Okay, wait, all of them are sums, right? And now no, wait, there's no problem with but yeah, okay, I think this is double sum. There is sum in this way as well, in direct way as well. Okay, now fine, I got it. Now we see that this is actually a zeta of 2, this is zeta of 3, this is zeta of 4, except that the first term is not there, right? If we sum the first term, we will get zeta of 2 minus 1 by 2, right? If I just take 1 by 2 common from for summing the first one, I just get zeta of 2 minus 1, right? And from here I get 1 by 3 times zeta of 3 minus 1, right? Because the first term is not there. And plus 1 by 4 times zeta of 4 is not there, right? And 1 by 5 times zeta of 5 is not, I mean first term is not there, right? So I get this sum. Now again I can write this as an infinite sum from n equals to 2 to infinity of zeta of n minus 1 by n, right? Now we will try to find this sum. Now I think I made a blunder. Like I could have just begun from here. Earlier in the solution, because I had knew that we will get this expression, so I tried to come over here. But I think it's easier to just go from here itself. I don't think we need to come here. Okay, now over here, let's go over here. I think this is because it's just because I had solved it earlier on my own where I got here, so I did that. But actually, we don't need to come here. From here itself, we can solve it. Okay. Okay, now from here, if you want to sum this, wait, I'm realizing a lot of details over here. This is actually kind of circular. I realize it now. This is actually kind of circular. I realize it now, but wait, I'll not tell you. Okay, fine. I'll just go with it. If you realize, fine. I'll say, or else this is completely good to go. Okay, now this one, we can sum it, yeah, because we can sum it in this way. Sum from n to infinity. Now, first of all, what I can do, 1 to infinity. Now, what I can do is, for this one, what I can do is, I can add 1 by n over here. 1 by n by 1 plus 1 by n square by 2 plus 1 by n cube by 3 and so on, and subtract minus 1 by n, right? And now we know that this sum will be equals to sum from n equals to 1 to infinity of, this will be minus ln of 1 minus 1 by n minus 1 by n, right? I'm summing this up. And then now we know that if we sum this up, let's say I want to take a limit n goes to infinity. Well, let's say because n is already, let's say k goes to infinity, and then sum from n equals to 1 to k of minus ln of 1 minus 1 by n minus 1 by n. We have this thing, right? Because I have just changed this to limit so that I can sum the telescoping sum over here. This is easier. Yeah. Now infinity. Now if we sum this up, we know that the sums of ln will get inside as product. So minus ln of this is n minus 1 by n minus 1 by n. You see that this is, both of them are, I mean the first one is telescoping. I'll show you how. Okay, wait, I have not sum it up. Sum from n equals to 1 to k. Limit k goes to infinity. Now this will just be, if you sum this, minus ln of wait, this was supposed to go from 2, right? 2, see, 2. Okay, now 2 minus 1 by 2, 1 by 2, and when it's 3. So see, like there is a sum, but because ln changes the sum to the product, so that's why all of them will be in product. Please note that. Don't be confused. Now 2 by 3, 3 by 4, 8k. This will be k minus 1 by k, right? And there's a minus sign. Don't be confused. Now over there, here it's a harmonic sum up to k, but we don't have first term, so this is harmonic sum up to k minus 1, right? So see the benefit of writing k over here. If it was infinity, that would have been so weird as infinity, and that would not have made sense because that goes to infinity and like wouldn't be good. But over here, because with this whole thing is being summed, even though this might diverge, the difference might converge, right? So that's the benefit. I think you get that. Now limit k goes to infinity of this is minus ln of 1 by k, which is ln of k. And this is minus h of k plus 1, right? This is limit k goes to infinity. Now this is 1 minus h of k minus ln of k. Yeah, and we know that when k is going to infinity, the infinite harmonic number minus ln of the infinite, this difference like converges to the Euler Mascheroni constant, which is irrational number, and approximated at 0.55772, something like that, right? So this is 1 minus Euler Mascheroni constant, and since this is approximately 0.577, this value will be approximately 0.423, right? So that's how I know that, that's how I found out that this series which is bigger than the given series, this is equals to 0.423. So that's why the series of the prime numbers should be less than 0.423, and since this series is between 0 and 0.423, in between, like it should converge to a value in between. So this convergent series, right? And so okay, wait, its value is not 0.423. Its value is some number k such that the k lies in between 0 to 0.423. I should write it in this way. It should be somehow more formal. Now, yeah, and anyhow, because this we have showed that this is bounded, so this is converging, right? I mean, because the value lies in between, so this should converge. And so because the divergent is equals to, I don't know, this one plus converging just a value, so this should diverge. So this is how the proof works. Yeah, while solving, I found something interesting. Yeah, please find that. You might also enjoy. Now, yeah, I hope you enjoyed the video. Thanks for watching. Finally, if anyone is just like skipping to the end of the video, the answer is this also diverges. Yeah. Thank you. Thanks for watching, and look forward to seeing in the upcoming video with another great idea.